Welcome back, my friends. So before we get into the Kurzgesagt video, as I do in every video, come sign up for the two things I'm creating. KelVPN, a post-quantum VPN. It'll protect you from quantum computers. The alpha is so close, and it'll be free to use. So you should come sign up to get notified when it drops in the description. And then also, if you want a free daily newsletter breaking down all the latest science in a very easy, quick fashion, come sign up for the daily newsletter at thedailydancenews.com, and I'll write it and send it to you every single day. So yeah, come get involved. Anyway, let's get into the video. Alrighty, what is dark matter and dark energy?
Matter, as we know it. Atoms, stars and galaxies, planets and trees, rocks and us. This matter accounts for less than 5% of the known universe. About 25% is dark matter and 70% dark energy, both of which are invisible. This is kind of strange because it suggests that everything we experience is really only a tiny fraction of reality. But it gets worse. We really have no clue what dark matter and energy are or how they work. We are pretty sure they exist though. So, what do we know? Dark matter is the stuff that makes it possible for galaxies to exist. When we calculated why the universe is structured the way it is, it quickly became clear that there's just not enough normal matter. The gravity of the visible matter is not strong enough to form galaxies and complex structures. Stars would more likely be scattered all over the place and not form galaxies. So we know there is something else inside and around them. Something that doesn't emit or reflect light. Something dark. But besides being able to calculate the existence of dark matter, we can see it, kind of. Places with a high concentration of dark matter bend light passing nearby, so we know there's something there that interacts with gravity. Right now, we have more ideas about what dark energy is not than what it is. We know dark matter is not just clouds of normal matter without stars because it would emit particles we could detect. Dark matter is not antimatter because antimatter produces unique gamma rays when it reacts with normal matter. Dark matter is also not made up of black holes, very compact objects that violently affect their surroundings, while dark matter seems to be scattered all over the place. Basically, we only know three things for sure. 1. Something is out there. 2. It interacts.
So that first one I have a problem with because that is not something we know for sure. Dark matter might not actually exist. We just might be looking at things in the wrong way. You might have heard of modified Newtonian dynamics and things like that. So there really is the possibility that dark matter just doesn't exist. And we're looking at things, very badly.
Dark matter is probably made up of a complicated exotic particle that doesn't interact with light and matter in a way we expect, but right now, we just don't know. Dark energy is even more strange and mysterious. We can't detect it, we can't measure it, and we can't taste it, but we do see its effects very clearly.
So basically, we call it dark energy because the term we have to introduce in the famous, Einstein's field equation for general relativity has units of energy.
In 1929, Edwin Hubble examined how the wavelength of light emitted by distant galaxies shifts towards the red end of the electromagnetic spectrum as it travels through space.
Edwin Hubble actually restores my faith in humanity a little bit because he started out a lawyer and became an astronomer.
He found that fainter, more distant galaxies showed a large degree of redshift. Closer galaxies, not so much. Hubble determined that this was because the universe itself is expanding. The redshift occurs because the wavelengths of light are stretched as the universe expands.
So what he basically saw was everywhere he looked, at every single galaxy, they were basically all moving away from us. And the further away he looked, the faster it was moving away from us. So think about this. All around you, everywhere you can see, galaxies are moving away. Further away, they're moving faster. So that kind of suggests this thing is expanding, right?
Recent discoveries have shown that the expansion of the universe is accelerating.
So that recent thing that showed us it's actually accelerating was using white dwarfs and supernova explosions. And we can use this as kind of like a standard candle, we call it, for distance measurements. And we basically found that, it's accelerating. The further you look back, you can imagine how you could just detect this by, using a measurement and then further where how much it should be. So you can look at this and realize, this dark energy is actually making the universe expand quicker.
It was thought that the pull of gravity would cause the expansion to either slow down or even retract and collapse in on itself at some point. Space doesn't change its properties as it expands.
So this stuff, dark energy, actually has negative pressure, we think. And this means that gravity behaves as though it's like repulsive. And so like a crude, not really appropriate analogy is like a bubble in the sea rising because of gravity. And so as a result, dark energy basically has this interesting property where its density remains constant even as it expands, right? And so here's the way it works. When gravity acts on stuff with positive pressure, it compresses it, right? Self-gravity compresses a cloud of gas into a much more compact object, aka a star. And so the work done by gravity appears as increased pressure and temperature. But when gravity does work on stuff with negative pressure, like dark energy, it causes it to expand, right? And the work done by gravity, in the case of dark energy, it produces more dark energy. And so the density of dark energy doesn't decrease even in an expanding universe. And so there you have it. We start with an expanding universe with lots of matter and a little bit of dark energy. And at first the expansion keeps slowing down because of gravity. But as time goes on, the density of matter keeps decreasing, whereas the density of dark energy just doesn't. So eventually you reach a point where the density of matter falls below that of dark energy. And from that point on, the repulsive behavior of dark energy basically dominates. And so instead of slowing down, gravity accelerates expansion. And so in our 13.8 billion year old universe, this turning point happened roughly between like 4 to 5 billion years ago.
More of it, new space is constantly created everywhere. Galaxies are tight-bound clusters of stuff held together by gravity, so we don't experience this expansion in our daily lives, but we see it everywhere around us. Wherever there is empty space in the universe, more is forming every second.
So this dark energy looks like it's a very, very weak thing because, where we see baryonic matter, typical matter, gravity seems to be way stronger and, it pulls stuff together. But over large distance scales, it seems like this dark energy takes over and it's kind of like an opposite gravity. It looks like it's pushing things away. So what he's saying here is kind of incorrect. We don't know if that's happening. It could be. So I'm bringing this up because people think, like here where we're walking around, there's new space emerging or something, or the universe is getting expanding. But that's just not happening in regions where there's baryonic matter, it looks like, at least.
So dark energy seems to be some kind of energy intrinsic to empty space. Energy that is stronger than anything else we know and that keeps getting stronger as time passes by. Empty space has more energy than everything else in the universe combined. We have multiple ideas about what dark energy might be. One idea is that dark energy is not a thing, but just a property of space. Empty space is not nothing, it has its own energy. It can generate more space and is quite active. So as the universe expands, it could be that just more and more space appears to fill the gaps, and this leads to a faster expanding universe. This idea is close to an idea that Einstein had back in 1917 of a concept of a cosmological constant, a force that counteracted the force of gravity. The only problem is that when we tried to calculate the amount of this energy, the result was so wrong and weird that it only added to the confusion.
All right. Let me give you some of the, leading candidates for what dark energy could be. But just remember that we really don't know what it is. So it could be a cosmological constant, a constant of nature, arguably like a fundamental property of empty space, right? If it exists. It could be vacuum or 0-point energy of all the quantum fields of the standard model of particle physics, and as such it would be like a fundamental property of the vacuum, empty space. It could just be the self-interaction energy of like a yet to be discovered scalar field. But chances are dark energy is something else altogether, and perhaps it doesn't even exist. Like, maybe the data implying it cosmic expansion is, just a little bit misinterpreted. We won't know until we know, I guess. And so far, attempts to detect it or discover its, true nature are pretty hopeless. Just an FYI, the vacuum energy would be a pretty ideal candidate, but unfortunately the predicted vacuum energy density is like 120 orders of magnitude too big, resulting in probably the greatest discrepancy between like theory and observations in the history of physics, the so-called cosmological constant problem. A lot of people call this the most embarrassing problem in physics.
Another idea is that empty space is actually full of temporary, virtual particles that spontaneously and continually form from nothing and then disappear into nothing again.
So this isn't something he should have put in here. Virtual particles, they're not real. That's why they're called virtual, for one. They're just like this calculational tool we use in quantum field theory. We don't actually think that's what's happening. There's different ways to look at these things, but it gets really complex because to describe fields in quantum field theory takes some strange math, and there's no analogy to a quantum field in our real world. Like, I can't tell you it's just like a wave, because a quantum field is not like a wave. So people just present this virtual particle thing because it's something you can imagine, whereas what's really happening is vastly different.
The energy from those particles could be dark energy. Or maybe dark energy is an unknown kind of dynamic energy fluid or field which permeates the entire universe, but somehow has the opposite effect on the universe than normal energy and matter. But if it exists, we don't know how and where, or how we could detect it. So there are still a lot of questions to answer.
We don't know if laws of physics are even the same, on the other side of the universe. These are things we're still figuring out. Recent studies have tried to look at the fine structure constant, which is kind of like the strength of electromagnetism, light. The thing that's holding all atoms together essentially and stopping you from falling through the floor, and it's responsible for your brain working and essentially everything, right? We're trying to measure this fine structure constant, which has this really weird value, by the way, 1/137. It's kind of the number you would use if you wanted to communicate with aliens, okay? It's just this mysterious number at the bottom of physics that no one understands. And fun little trivia fact, in Rick and Morty, C137, the universe, that's where they're getting this from. And so we're trying to measure this fine structure constant, on the edges of as far as we can, essentially, okay? So to see if it's the same, to see if the laws of physics are the same everywhere.
Our theories about dark matter and dark energy are still just that, theories. On the one hand, this is kind of frustrating. On the other hand, this is frontier science, making it very exciting. It shows us that no matter how much we feel we're on top of things, we're still very much apes with smartphones, on a tiny, fragile island in space, looking into the sky, wondering how our universe works. There is so much left to learn, and that is awesome.
It's like what Einstein said, the most beautiful thing we can experience is the mysterious. And what's more mysterious than dark energy and dark matter? Maybe consciousness, but yeah, they're definitely up there. So I feel like people generally want to hear more about what we do know instead of what we don't know. So I don't want to sit here in these videos the whole time saying we don't know. Because, with dark energy and dark matter, we don't know. And dark energy is kind of just like a placeholder for something we have no idea about. But something we do know about dark energy is that it looks like it's the only thing in the universe that can escape black holes. That's right. Dark energy, black holes don't have any impact on dark energy. And this is basically because dark energy isn't affected by gravity. Dark energy kind of, acts in an opposing way, we think. Anyway, that'll do for today's video, guys. I don't want to talk too much about all this stuff we don't know. We could talk about all the different kinds of theories floating around and all the different ideas, but none of it is, we just don't know. So I don't want to talk for too long.